Hi, this is the third lecture of this advanced geostatistics course on spatial uncertainty assessment. And in this lecture, we'll see methods to estimate local distribution functions, which is a fundamental step of most of geostatistical simulation methods. Let's recap. The stochastic simulation methods for continuous variables, most of these methods are based on two fundamental steps. In the first one is estimation of local conditional distribution functions. In a second step, we generate values from those local conditional distribution functions through a Monte Carlo method that you have seen before. So, continuing recap, we know how to calculate with ordinary kriging by ordinary kriging of original variable the most probable value at any spatial location. But now, as we're going to see, we want to calculate the distribution functions at some spatial location. So let's see a very simple and naive example. Let's estimate the extreme values of this variable here, the set of values in area A. Okay. The estimator of the mean, arithmetic mean, is, let's say, 56.6. Now, if I ask you what is the proportion of values below 25, and you easily say 2 over 9.22. What we mentally transform the original values in binary values before calculating the ratio. Let's see. So values lower than 30. You see, this is 1, 0, 0, 0, 0, 0, and we count two values over 9. Okay, the same, for example, the proportion below 70, you do the same, 1, 1, 1, 0, 0, 1, 0, and so on, and we count 6 ones over 9 values. So, those global proportions of area A were calculated by a binary transformation. Now, we can do the same, but now for a spatial location x0, for example, this one. I want to know the probability, for example, of x0 to be lower than 30%. And we can do, now it is not arithmetic mean, but a weighted average with sample values with different weights. More regarding, they have more weight regarding the proximity to the target, the target location, and so on. So we transform those values first in ones and zeros, and we do a weighted average of ones and zeros. Okay. So we can calculate any probability. So a probability lower than 50, 80, 200, and so on. And we do the same procedure. We transform in a binary variable according to this result here, 50 or 80 or 200, and afterwards we calculate the weighted average of this binary variable. So, and in that way, what we did, let's say we create a binary variable, let's call indicator variable, high, with this small z. Z is the result, the class, the limit of a class that you want to calculate, the class of original variable. So this variable, this high indicator variable takes the value 1 if z of x is lower than z or is 0 otherwise. Okay, so this is crucial to understand. By transforming the original variable z in an indicator variable high, any probability class of z can be assessed with the first moment of high, with the mean. Okay, you see? So this is extremely important for the first formalism, which is the indicator formalism. Let's see the probabilistic model of this new formalism. So in a first step, z of x is transformed in a random variable I of x with a function of a result z here, 1 or 0, sorry. It takes value 1 if z of x is lower than z, otherwise it's 0. So the expected value of I of z is equal to the probability of any value z, the original variable, to be lower than z. You see, that's what I have seen before. Now, any value of our cumulative distribution function of original variable can be described in terms of a first moment of the new variable created here, okay, of the indicator. So the idea is to estimate the cumulative distribution function of z, or all classes of this cumulative distribution of z, original variable, through an indicator variable I of z. Okay, so estimate the class of fz, which is the cumulative distribution function of z, is the same of estimate the mean of I of z. Okay, the mean. Here's the mean of the indicator variable, and this is the variance here, which is a function of the mean. The variance is no else of this indicator, is no else than the mean minus the square of the mean. Let me tell you that the maximum minimum value of the mean is 0, 1, of course, because the variable itself is 0 or 1. And the variance goes from 0 to 0.25. 0.25 is maximum value of the variance, indicator variance, which sorry, this is a mistake here, which is corresponds to those situations where you have 50% of zeros and 50% of ones. Okay, and this is the variance in this case is. Now we can calculate the variograms and covariances of indicator variable. This is the variogram, the square of difference between two values separated by a vector h. This is a spatial covariance expression, and this is the relationship between the variogram and the covariance. So now we can perform the ordinary kriging of the indicator, which is the indicator kriging. So at each spatial location x0, we have already seen that is the probability of the original the probability of any class of the CDF of original variable. So this can be estimated by a linear combination of a neighborhood samples through this linear combination here. Okay, we can apply to calculate this linear combination of surrounding samples I of z of x alpha with the two basic criteria of kriging estimators, the biasness and minimum of summation variance. Here's the expression of. So it's a classical procedure. We first write the estimation variance in terms of the covariances, the covariance of indicator, covariance of indicator variable here, and when we minimize this this variance here, the estimation variance will lead to the classical system of equations of ordinary kriging of indicator. Okay, the CDF can, so in short, the CDF original variable at location x0 can be assessed with the ordinary kriging of the indicator. This is an example. So, and this is how the indicator formalism works. In any location, we estimate the key classes of, for example, at a location x8 here, which is based on indicator formalism. So to estimate each class, we have to calculate and model the variograms of each indicator. You create here, for example, 1, 2, 3, 4, 5 indicators. We have 5 models of variograms, and we have to calculate and model those variables. Okay, so this is basically, in a simple way, and how the indicator formalism works to estimate local distribution functions of original variable z of x, porosity, continuous variable, sorry, porosity, permeability, metal grades, and so on. What are the advantages of this method? The advantage of this, the main advantage is the spatial continuity of extreme values can be quantified by the indicator variograms. So as you calculate the variograms, for each class, we guarantee that the spatial patterns, when you have a high continuity, which is not very common in extreme values, they are reproduced. What are the drawbacks of this method? Well, this order relation, which is when you have a result z1 lower than z2, fz1 is lower than fz2, must be. But as we estimate separately each class, this order relation is not cannot sometimes be observed. But this can be corrected a posteriori. It's not a huge drawback. The main one is this one, the second. The need of modeling variogram for all classes. This is a cumbersome task, and we sometimes, in extreme classes, we do not have high continuous structures, and it's not easy to calculate variograms for the extreme classes. And there's one version of this indicator which is medium indicator kriging, which means that in this case we calculate just one variogram for the medium, and which normally works well, and we adopt this variogram for all classes. But again, if we do that, we lose the advantage that I've mentioned. Now let's see another method, which is a parametric approach called Multigaussian kriging. Let's assuming that y of x is a Multigaussian variable, which means that is Multigaussian distributed. So the cumulative distribution function g of I of this Gaussian variable at any point is totally determined by the conditional expectation here in any location x0, by the conditional expectation and the conditional variance here. So the CDF is totally defined here by those two parameters, the mean and local mean and variance. Okay. So the conditional expectation is equal. This is it is demonstrated. This is a fact. I do not do that in this lecture, but the conditional expectation of x0 is equal to the simple kriging of y, because this is multi-Gaussian distributed. So this is equal to the simple kriging, the mean, okay, the conditional expectation, and the variance is equivalent to the to the kriging variance. Okay, so at any location, at any local CDF of y is totally defined by the simple kriging estimator and variance. Okay, this is the mean, local variance obtained by the simple kriging of y, and that's it. And I totally define the cumulative distribution function at that location y0. Okay, extremely simple, just one kriging, simple kriging, and we define. Now the problem is we do not have multi-Gaussian variables and neither a Gaussian distributed variable. So we have first to transform our original variable, our porosity, permeability, whatever, in a Gaussian variable. Transform those values in a Gaussian variable. For that, there are several methods to do that. This is represented here, uniform transformation, which means that the values of my variable z, the original variable z, are transformed through the cumulative distribution function. So they are equivalent to the Gaussian value with the same CDF probability, cumulative probability. Okay, so this is represented in this sketch. We have those original variables are transformed in a standardized Gaussian variable. But let me call your attention to this. I transformed my original variables in Gaussian, but I have to assume that they are multi-Gaussian distributed. This is a hypothesis that cannot be validated. I mean, multi-Gaussianity. This is some kind that I assume, and well, at the end we have to pay attention to, because there's always a bill to pay. So how it works? We transform. We have now our variable, our Gaussian variable. At any location, we do the simple kriging with the surrounding sample values. For example, in this case, we have a mean 2.8, local mean 2.8, and the variance 1.5, which is represented by the local CDF here, which corresponds to, well, high estimated mean, high variance. For example, in this point here, just so low values, surrounding low values, and very far from the target, we have a low estimated mean, okay, because those values are low, and the low variance, okay. So in the third step, after we estimate the local distributions everywhere, what we in any location of a grid of our regular grid of points, we have to transform back my Gaussian distribution function into original distribution function through the transformation, the uniform transformation that we have used before to transform the original variable in Gaussian. You do the same, we do the same for the other, and so on. So this is as for multi-Gaussian kriging. What is main advantage? Simplicity of implementation. As a matter of fact, this is the most common method in any commercial software because it's simple to apply. But this simplicity hides, sometimes a truth that is not convenient truth, which is the most of the users do not know exactly what they are assuming, what are the assumption, the main assumption of this method, which is the multi-Gaussianity. Okay, what are the drawbacks of this method? The multi-Gaussianity hypothesis of the Gaussian variable cannot be validated, must be assumed, and that's it. The second is the spatial patterns of extreme values are not reproduced. In fact, just one model of transformed variable y is needed for Gaussian kriging. That's why it is very simple to implement. So Just to summarize, kriging methods allow the parameters estimation, mean and variance, percentiles of local conditional distributions, crucial step of most stochastic simulation algorithms. For example, in this case, those two methods give rise to indicator kriging of continuous variables, give rise to sequential indicator simulation of continuous variables with high spatial continuity of extreme classes, the advantage of the method. Multi-Gaussian kriging give rise to the sequential Gaussian simulation, as we are going to see.